fundamental theorem of calculus is giving us a two-part process to come up with an answer. And for those of you that took calculus in a previous life, this is the part that finally starts to look normal. All the stuff with rectangles maybe looked less normal, but fundamental theorem of calculus says, step 1, find the antiderivative. So it's kind of like this integration symbol and the dx part are saying, look what's in between us. Whose derivative is that? So if I'm looking at 3x squared plus 2x and I'm saying whose derivative is that? Well, this is the derivative of x cubed. And 2x is the derivative of x squared. And then that second part of the fundamental theorem of calculus, the b minus a part, says we're looking at this, we're looking to evaluate this from 1 to 3. And step 2, we're going to plug in the numbers. So in this case, I'm going to plug in the 3 and have 3 cubed plus 3 squared, and then subtract off, plugging in the 1. 1 cubed plus 1 squared. And maybe we get to walk away, or maybe we're supposed to simplify that to an actual number, right? But there's this two-step process to use the fundamental theorem of calculus. So if you haven't quite finished step written homework 1, just know that that last question where he's asking you to use the fundamental theorem of calculus, this is what that means. That two-step process, find the antiderivative, and then plug in those endpoints. Now, the other thing that the fundamental theorem of calculus gives us is now, this is what happens if I have a definite integral, meaning I have endpoints on there. But if I don't have endpoints to plug in, then we just stop at step 1. And we're finding an antiderivative function instead of an actual value for a definite integral. So I'm going to erase this. And really, we're going to practice some antiderivatives. And the first one, just like when we were taking derivatives, one of the first things we did was worry about like a number times x raised to a power. So same deal here. If I walk up to an integral and I'm looking at 5x to the 4th plus 20x to the 8th minus 3x to the negative 2, I'm going to say, hey, we're in good shape. I've got numbers times x's raised to powers. So that rule for my antiderivatives, so I'm going to add 1 to the exponent. I'm going to write them out this time, but I'm going to add 1 to the exponent and divide by the new exponent. Here again, I've got a number times x raised to a power. So I'm going to add 1 to the exponent, divide by the new exponent. I've got x raised to a power. I'm going to add 1 to the exponent and divide by the new exponent. And then when I get to the end, I'm not going to forget to write a plus c. Could you simplify some of these numbers? Absolutely. Right? 5 over 5, I don't need to write that. Negative 3 over negative 1, we could definitely simplify that. Suppose I got a little more fun, and the antiderivative that I was asking us to find, or the definite integral, sorry, the indefinite integral I wanted us to evaluate. Let's say I had e to the 5x. I know it looks interesting, it's not that interesting, but if I want the antiderivative of e to the 5x, we know that the derivative of e to the 5x is just e to the 5x. And the antiderivative is almost the same. Oh, I lied. I just did something wrong. Someone was supposed to catch my mistake. If y is equal to e to the 5x, what's y prime? Maybe that's hard to type in the chat. I'm going to see if anyone wants to type it in the chat. Or unmute yourself and tell me what the answer is. If I take the derivative of e to the 5x, what do I get? Yeah, there we go. Someone got the answer I got wrong the first time. This is e to the 5x times 5. Because thinking way back to 17a, that times 5 is coming from our chain rule, because I have to remember to multiply by the derivative of the 5x. So in general, when we're taking derivatives, we end up like multiplying by that number because of the chain rule. And when we're taking antiderivatives, we're going to end up dividing that number because we're kind of going backwards. And the going backwards for multiplication is division. So the antiderivative of e to the 5x is going to be e to the 5x divided by 5 plus a constant. Now, if you want to check your work, the relationship, that fundamental theorem of calculus says whatever we think the answer is down here, if we take the derivative of it, we're supposed to get the e to the 5x back. So if I made y equal to e to the 5x over 5 plus a constant, and I wanted to take the derivative, then that over 5 I could think about as saying 1/5. And then I take the derivative of e to the 5x and get e to the 5x, and then chain rule would have me multiply by 5, and the derivative of a constant is 0. I know I said that really fast, but the 5 and the 1/5 go away, and this matches what we have over there. Which means this was the antiderivative of e to the 5x. Good times. More fun antiderivative rules that we need to know. I'll start off with the boring one. So I walk up to this problem and I say, oh, hey, whose derivative is 1 over x? Whose derivative is 1 over x? We know this. We got this. At least more than one person has this, I'm sure. I know we're super excited and awake today. ln of x, I got a log, I got another ln of x. Thank you. I've been pausing, waiting. Lovely. Yes, it is natural log of x. Derivative of ln of x is 1 over x. And there's a real subtlety here when we're finding antiderivatives, and I want to point it out because WebAssign is going to be picky about this. So when I find the antiderivative of 1 over x, it's almost natural log of x. Oh, plus a constant. But we're going to have to adjust for something. And the thing we're going to have to adjust for is I want the domain of 1 over x to match the domain of ln of x. And right now they don't. So 1 over x, I can plug in anything except 0. But for natural log of x, I can only plug in positive values. And the way that we reconcile this is to put an absolute value around that natural log of x when we write the antiderivative. So the antiderivative of 1 over x, or the integral of 1 over x dx, is the natural log of the absolute value of x plus a constant. I want to rattle off just a couple more quick ones before we talk about some substitution. So, started off with the trig function. Let's have some more fun with trig. If I took the integral, or I'm trying to find the indefinite integral of secant squared t dt, I'm going to walk up to this and ask myself, hey, is somebody's derivative equal to secant squared? And you all are going to say, or type, My Zoom's not frozen. I'm just staring at the chat, hoping someone will save me with an answer. Whose derivative is secant squared? I'll give you a hint, it's a trig function. For the win, we got a tangent of x. Thank you very much. So I am looking at, except it won't be tangent of x because I put a t in there. So this is going to be tangent of t plus a constant. More fun trig. Let's say that I had cosine theta d theta. I walk up to this integral and I say, hey, whose derivative is that? And someone's going to write I like the question mark. Thank you for trying. Absolutely. Oh, maybe the question mark was supposed to be the theta. Yeah, totally. So the function whose derivative is cosine is positive sine of theta. If I were to take the derivative of positive sine, and I am intentionally switching the variables up on us because, as you all know, in the 17 series, everybody likes to switch the variables up on you. So if I take the antiderivative of sine of x, this is saying whose derivative is equal to positive sine, and the answer to that is negative cosine. Once upon a time, you all took first quarter calculus, and when you were sitting there in 17A, if we were talking about derivatives, you might walk up to that, and I bet a bunch of you would say, man, that's going to be a nasty quotient rule to take that derivative. Good news, we don't have a quotient rule for antiderivatives. Also good news, we have algebra skills instead. So when I look at this and I'm thinking, I want to find the antiderivative so that I can use that fundamental theorem of calculus and plug in the endpoints. But in order to do that, this thing is a mess of algebra. Sure would be nice if I could make this look like a number times x raised to a power minus a number times x raised to a power. So that's going to be my first line of defense when the antiderivatives get messy. So I'm going to rewrite this, and that square root of x that I have on the bottom, I can think about that square root as really being x to the 1/2 power, but because it's in the denominator, it's actually x to the negative 1/2 power. So I'm looking at x to the negative 1/2 power times 2x cubed minus x dx. So I have taken no antiderivatives yet. We do not have an antiderivative product rule or quotient rule. We have to do the algebra. So from this point, I'm going to take that x to the negative 1/2 and distribute it in so that I can make this look like a number times x to a power. I'm looking at 1 to 4. This will be 2x. And because everybody loves fractions, you know that when I distribute this in, I'll have two numbers with this, two things with the same base of x. So I'm going to add those exponents. So 3 plus a half, 3 is 6 halves, plus another half, that's going to be 7 halves. Oh, sorry, it was a negative, I lied. 6 halves minus a half is going to be 5 halves. Here, that x is raised to the invisible 1 power, which means when I combine those exponents, I'm going to have x to the 1/2 power. Now that I've worked this down to a number times x to a power, now we can use that first antiderivative rule that we talked about. I'm going to add 1 to the exponent, divide by the new exponent. So I am looking at 2x, and when I add 1 to the exponent, I'm going to be adding 2 over 2. So I'm going to have 2x to the 7 halves divided by 7 halves. And over here, I'm going to have x to the 3 halves divided by 3/2. We can clean that up or not, but I don't want to forget about the fact that we do have endpoints, meaning this is a definite integral. So that first step was to find the antiderivative, but now I know I'm going to be plugging in 1 and 4. So if we wanted to clean this up, dividing by a fraction is the same as multiplying by its reciprocal. Oh, and there's a question about the 7/2 exponent. So if I'm at 5/2 and I add 1 to the exponent, 5/2 plus 1, I'm really thinking about that 1 not as a 1, but really as a 2/2. And that's how I got that 7/2. So I've got 7/2 is the exponent. Dividing by 7/2 is the same as multiplying by 2/7, which is going to, by the magic of my eraser, turn this into 4/7. And dividing by 3/2 is the same as multiplying by 2/3. So when I plug in those endpoints, I'm going to end up with 4 times 4 to the 7/2 over 7 minus 2 times 4 to the 3/2 over 3 minus, and now I'm plugging in the 1. 1 raised to any number is going to be 1. So I'm going to be lazy when I plug in the 1s, and I'm not going to write all the exponents out. That's going to look like 4/7 minus 2/3. Now, I've also been getting some questions both by email and in office hours. Yeah, if you don't get a calculator, quit here. It's not worth your time. Could you simplify this without a calculator? Yes, we could. It's not worth our time. Move on with your life. Certainly, if this were a quiz or a midterm kind of question, we would just leave it there. Okay, let's have some more fun with antiderivatives. Pausing just for a second. Watching for questions to pop up. Seeing no questions. Going to erase me. Oh wait, I had, just a second, had the book pulled up a second ago. It's just super tiny on my screen. So let's say that I've got another one here. Let's keep the numbers pretty easy. No fractions yet this time. We need instructions. So same instructions as last time. We're going to evaluate this definite integral. So the integral from 0 to 2 of the quantity y minus 1 times the quantity 2y plus 1. We just said that we don't have a product or quotient rule for integrals, which means we get to use our algebra skills again. If I have to integrate this, I'm hoping to make it look like a number times x raised to a power. And the only way that I know how to do that is to multiply that out. If I start multiplying that out, or foiling it out, or you could do box method, however you want to multiply, I'm going to get y times 2y, so 2y squared, plus y times 1, minus 1 times 2y, and minus 1 times 1. You have a choice. We can combine those y's first or integrate each part. I'm going to combine them so that I end up with 2y squared minus y minus 1. All that work was just the algebra part so that we can get to the fundamental theorem of calculus. First part of that fundamental theorem of calculus says I'm going to find the antiderivative. And the antiderivative of 2y squared, I'm going to add 1 to the exponent, divide by the new exponent. Antiderivative of negative y, there's a secret invisible 1 for an exponent there. So I'm going to end up with y squared, because I'm adding 1 to the exponent, over 2. Now, the negative 1, there are a couple of different ways to think about this. One option is to think about this having an invisible y to the 0 power. I think that's weird. It's not wrong. I just personally prefer to look at that negative 1 and say, whose function has a derivative of negative 1? Negative y. That's who has a derivative of negative 1. Because it's a definite integral, I know that I'm going to be plugging in these endpoints. Notation-wise, I've been doing this, but I didn't explicitly say it. When we're using the fundamental theorem of calculus, after we've taken the antiderivative, if it's a definite integral and I have limits, the notation that we use is a vertical line, and we just copy those limits right over. Now we're ready to plug them in. When I plug in the 2, I'm going to do the arithmetic kind of fast here because the numbers aren't terrible. When I plug in the 2, 2 cubed is 8, times 2 gets me to 16, divided by 3. Plugging in the 2 here, 2 squared is 4, divided by 2, and back to 2, and minus another 2. When we plug in the 0, I'm going to get 0 minus 0 minus 0. I'm taking a minute to actually write those zeros out because sometimes, especially with the WebAssign problems, there are functions that when you plug in 0, you don't get 0. So it's a really easy tripping point for students who are like staring at this problem and putting it in 12 times and then realizing that that was the problem. Do I need to simplify this? Probably not. Could we? Yeah, they're not terrible fractions. Okay. The first thing that I do when I walk up to an indefinite integral, or if I'm trying to find an antiderivative, the first thing that I'm hoping is that I can do some algebra to make it look like numbers times x's raised to powers. But I have a problem here because there's trig in my way. And there's no algebra I'm magically going to do to trig that's going to turn that into x's raised to powers. So the next trick of like a question I'm going to ask myself is, does the derivative of one part equal the other part? And here's what I mean by that. I would like super quickly ask everybody to just raise your hands, but I'll just pretend I know the answer. How many people have studied a language other than English in school? Yay, everybody raised their hands because y'all graduated from high school. You're at Davis. You know some bit of some other language. Well, math is kind of another language. And when I look at this problem, what I'm going to do, this is like someone, let me pick a language I don't know. I do not speak Finnish. So I think, yeah, I don't speak Finnish. So imagine that I'm sitting in like my first class in Finnish, and the teacher has just asked me this question in Finnish. And it kind of looks like, whoo, garbage. I have no idea what that means. So I'm going to pull out my dictionary. And in my dictionary, I'm going to convert the words from Finnish into English, because that's my native language. And so I'm going to convert into English. I'm going to figure out the answer to the question. And then when I'm done, I'm going to have to use my dictionary again to write the answer in Finnish. Well, that's how I think about attacking this indefinite integral. So I've got something here, and I'm going to build my vocabulary list off to the side. And here's what I mean. This has a couple ugly parts. You might argue the cosine is ugly, but really, I got a 3x squared, I got a cosine, I got an x cubed, I got a dx. There's all kinds of stuff going on in there. And I'm going to start my vocabulary list by letting you be equal to x cubed. And there's a reason I'm doing it, and we'll loop back around to that original question that I said, which was, does the derivative of one part equal another part of the problem? Well, the derivative of x cubed is 3x squared. So that piece whose derivative is in the problem somewhere, I'm calling that u. Then I'm going to build my vocabulary list over here. And I'm going to say, well, if that's what u is, then I know I need a dx, which means I'm going to have to take a derivative. And du dx, if I take that derivative, is 3x squared. Usually, when we're working through u substitutions, we're working with antiderivatives, we're actually going to not write out this step, and instead, we're going to write this in its differential form, which is du is equal to 3x squared dx. Now I'm thinking about this vocabulary list, and I'm saying, hey, that 3x squared and the dx, I know what I can call it. I can call it du. So the 3x squared and dx becomes du when I'm translating this. And that x cubed right there, well, I know based on my vocabulary list that I can swap out x cubed for u. So this becomes cosine of u. Now, instead of this integral that looked really messy, I instead have this integral that I can probably figure out. Whose derivative is cosine? Sine. So I'm going to find that antiderivative and get sine of u plus a constant. But back to my analogy, this is like I translated the question so that I could answer it, but the teacher asked me the question in the language of x, so I have to return my answer also in the language of x. So my last step here would look like sine of x cubed plus a constant to return it back to the same language that we used at the beginning. I walk up to this integral and I say, oh, hey, it's just algebra. I bet I could multiply that out and make it look like some number times t raised to a power. And then I go to the 10th. Heck no, it's going to take me all day. Multiplying out t to the 4th plus 7 to the 10th power. I don't think so. So I'm going to pull out my dictionary. And in my dictionary, I'm going to say, does the derivative of one part equal another part? Why, yes, it does. The derivative of t to the 4th plus 7 is equal to 4t cubed. So I'm going to build my vocabulary list over here. And if u is equal to t to the 4th plus 7, then that differential form of my derivative would look like du is equal to 4t cubed dt. Then I return to my problem and I say, I need to use what's in my vocabulary list to convert everything. So 4t cubed dt, that's equal to du in my vocabulary list. And that t to the 4th plus 7, that's what we call u, which means this piece becomes u to the 10th power. I'm going to answer the question in my simplified language, meaning we're going to find the antiderivative in our u language. So I'm going to add 1 to the exponent, divide by the new exponent, plus a constant because it's not a definite integral. And then my last step, I've got to convert this back so that it's written in the same language that the question was asked in. It was asked in the language of t's. I need to take it back to the language of t's. So I would have t to the 4th plus 7 all over 11 plus a constant.